Hello and welcome back to Introduction to Number Theory. Now, we will prove that for prime numbers there exists a primitive root. Actually, we will prove a more general statement. First, let me remind you of what order is. We consider the set of remainders over prime number, remainders modulo prime number. We denote this set as z over p z, where p is the prime number. And not all of them are interesting to us. However, the complete set looks like this: 0, 1, 2, and so on, p minus 1. And order of an element modulo p is the least positive integer power to which we should raise this element in order to obtain 1 modulo p. We understand that p minus 1 is divisible by order of any of these elements. Well, not all of them have an order, or all except for 0. So now let's remove 0 from this set in this specific way. If we remove 0, we obtain a multiplicative group of a finite field. The question is, are all divisors of p minus 1 good for being an order of some element of these? How many elements of specific order are there? Let's denote by psi of d the amount of elements of order d. So it is the number of elements, well, from here, of course, such that order of this element A is precisely d. So the question is psi of d equal to 0 for some d divisors of p minus 1? Well, of course, d should be a divisor of p minus 1. p minus 1 is divisible by d. For some divisors, is psi of d equal to 0? Can we state that for all of them psi of d is greater than 0? And last but not the least, can we say to what psi of d is equal to? Well, first, let's notice one obvious thing. If we take psi of d for all divisors of p minus 1, we will get what we will get. We understand that for any of these elements, its order is a divisor of p minus 1. Psi of d is the number of elements of a specific order. So over here, it looks like we simply group our elements by their orders. And this means that the sum of the number of elements of order d for all divisors of p minus 1 is simply p minus 1, because it is simply the number of elements in this list. Well, recall that we have a similar equality, similar property for Euler's function. The sum of phi of d over all divisors of p minus 1 will be equal to p minus 1. From this it follows that the sum of psi of d and the sum of phi of d are equal. And now we will prove that actually for any d, psi of d is equal to phi of d. No, not just for any, but those that are divisors of p minus 1. This will follow from the fact that psi of d is either equal to 0 or equal to phi of d. Well, if we prove that psi of d is either 0 or phi of d, then using the fact that their sums are equal, this will mean that none of these sums can be 0. Otherwise, this sum would be less than this one. Okay, so what can we say about psi of d? Well, it's either 0, then we already have this case, or it's greater than 0. If it's greater than 0, then there exists an element of order d. So consider this element. And consider an equation x to the power of d minus 1 equal to 0. Of course, this polynomial and this equation we consider within the field z over pz. We understand that it is an equation of degree d. So it has no more than d roots. At the same time, we have a, which order is equal to d. So we understand that a is one of the roots of this equation. Okay, so we have a. We obviously have 1 as one of the roots of this equation. So 1, a. Are there any more roots of this equation which we can right now write down? Well, of course, for instance, a square is also a root of this equation, because a squared to the power of d is also equal to 1 modulo p, because a to the power of d is equal to 1. And also a to the power of 3, and so on, and a to the power d minus 1. All these elements are roots of this equation. All of them are distinct roots of this equation. They are distinct because d is the order of a. So none of these can be equal to each other. Are there any elements among these with order d? Well, let's recall that order of an element of the form a to the power k is equal to d over the greatest common divisor of d and k. And if we wish for the element a to the power of k to have order exactly d, then this greatest common divisor must be equal to 1. But greatest common divisor of d and k is equal to 1 if and only if d and k are mutually prime. So how many such k's are there? Well, if k should be mutually prime with d, and k is a power between 0 and d minus 1, then we understand that there are exactly phi of d such k's. So in this case, we understand that all possible elements of order d are in this list, but not all of them have order precisely d. Only those of them that are the form a to the power of something mutually prime with d. Well, this means that there are exactly phi of d elements of order d. So in this case, psi of d is equal to phi of d. So finally, it's either 0 or it's equal to phi of d. So since sums are equal, then it holds that phi of d is always equal to, well, psi of d is always equal to phi of d. And finally, as a simple corollary, there exist primitive roots modulo p, and they're exactly phi of p minus 1 primitive roots modulo